Let's do example 11.50. So we have a uniform 8-meter, 1,500 kilogram beam, and it's hinged to the wall and supported by a thin cable attached 2 meters from the free end of the beam. The beam is supported at an angle of 30 degrees above the horizontal, and they want us to draw a free body diagram, find the tension in the cable, and figure out how hard does the beam push inward on the wall. Okay, so the first thing we're going to want to do is draw that free body diagram. Whenever we do a torque free body diagram, draw it big. There's a lot of stuff going on in here, and so we want to make sure it's big enough that we can see everything. All right, so let's start with those forces that we have. So one we have is we do have the tension here. We also have, because it's a uniform beam, we are going to have gravity acting at the center. And then we do have the wall, and so the wall is applying a force out. I'm going to call it Fx. It's also applying a force up, Fy. Now, if you didn't know which way the wall is going to apply a force x and in the y, and we're just resolving into components here, that's the idea. If you guess wrong, what you're going to find out is, like, if I get a negative value for Fx, I just picked wrong. Because sometimes the wall actually need to hold that beam to it, or it'll need to push down. In this case, I can imagine that if I had that beam supported there by this string, and I let go of here, which way would it go? It would fall down, and that tells me that the Fy is up, and it would push against the wall. It's trying to slide into the wall, so I know the wall's pushing out. Okay, so we have our forces, so now we're going to go ahead and generate a torque equation. Now, whenever we generate a torque equation, the first step is we need to identify all of the forces. Check. I also need to know their distances. So this distance here was 2 meters. This distance here is also 2 meters. And then this distance down here is 4 meters. So that is my total of 8. I also need to choose an axis of rotation. So I'm going to go ahead and choose my axis of rotation here at the corner. The benefit of choosing it there is the Fx and the Fy, those two components, are not producing any torque. The only things producing torque are the tension and gravity, and I know what the mass is, so I should be able to find the tension from that torque equation. Now, remember, our torque equation, I need the perpendicular components of these forces to my beam. So we're going to have to go ahead and resolve them into components. So let's go ahead and do that in blue here. So we're going to resolve mg into components. So I'm going to have an mg, and this angle here is 30, so we'll call that 30. So this will be mg cosine of 30 here, mg sine of 30. I really only need the mg cosine of 30. I only need the perpendicular component because the one that's parallel isn't going to produce any torque. And then my tension, resolve that tension into components. So I'll have T sine of 40 is my next one here. Okay. So let's go ahead and generate our torque equation. So summing up the torques, set it equal to 0 because it is not angularly accelerating. And so I need to decide, are they going to be positive or negative torques? So I can use my right hand rule. So I will point with my right hand from the axis of rotation to the force, push my F finger in the direction of the force, and so for T sine 40, it's coming out of the board, so it would be a positive. The mg cosine 30 is pointing into the board with my thumb, so it would be a negative. The other way to do that is push like you are and see which way does it rotate. I'm rotating this clockwise, so this mg cosine 30 is negative, and this one's rotating it counterclockwise, so it's positive. So I'll just put a little negative sign and a positive sign to remind me of that. Let's go ahead and generate that equation. So I have mg, well, let's do the other one first. T sine 40 times how far away it is from my axis of rotation, so it's 6 away, minus my mg cosine of 30 times how far away it is from the axis of rotation, it's 4, equals 0. So given that information, I should be able to solve for tension. So I get tension is equal to mg cosine of 30 times 4, all divided by sine of 40 times 6. Plug that into your calculator. You should get 13,204 newtons for that tension. Now, for part B, or part C we're on to, we're trying to find that Fx value. Well, it's not in my torque equation, so a torque equation isn't what I want to use for that, okay? What I do want to use is I do want to use a sum of the forces in the x direction. Okay, so I want to sum up the forces in the x direction. Again, it's not accelerating. So now I have to think about, okay, what forces are in my x direction? Is mg in the x direction? No. Is Fy in the x direction? No. How about tension? Well, partly. And so now I'm going to have to resolve tension yet again, but this time I need to go ahead and figure out what are its x and y components. Okay. So in order to do that, I see this angle down here is 30. So that angle here is 30. That makes this angle here 10. And so the x component here, this one, is going to be tension times the cosine of 10. All right. Notice I drew my free body diagram pretty big so that I could do both the blue, my torque resolving of vectors, and the red, my x and y resolving of vectors. So go ahead, plug that in. So now I have tension, or I have Fx minus tension cosine 10 equals 0. Solve for Fx. Fx is going to be my 13,204 cosine of 10. And so we should get a number here of 11,435 newtons for that tension in that cable.